In the intricate tapestry of electrical design and installation, the creation of a safe and efficient electrical system relies on a foundation of meticulous planning and precise calculations. Branch circuit calculations, a pivotal aspect of this process, lay the groundwork for determining the capacity, load distribution, and protection mechanisms necessary for the seamless flow of electricity. However, before delving into the specifics of load types, diversity factors, and equipment calculations, it is essential to establish a comprehensive understanding of the general requirements that govern these calculations. At the heart of these requirements lies a commitment to both safety and efficiency. The National Electrical Code, NEC, recognized as the benchmark for electrical safety standards, provides a comprehensive framework that outlines the fundamental principles and guidelines for branch circuit calculations. These requirements ensure that electrical systems are not only properly designed but also aligned with the highest standards of safety and performance. This section aims to illuminate the overarching principles that underpin branch circuit calculations. By exploring the general requirements mandated by the NEC, we lay the groundwork for a deeper exploration into the intricacies of load calculations, demand factors, conductor sizing, and other critical aspects. As we navigate through the landscape of electrical design, these general requirements act as our compass, guiding us toward systems that prioritize the protection of life, property, and the seamless functioning of our modern world. In the National Electrical Code, NEC, the general requirements for branch circuit calculations are covered in several articles that provide guidance on various aspects of electrical design and safety. Below are some of the key NEC article references related to general requirements for branch circuit calculations. Article 210, Branch Circuits. Article 210 in the NEC provides an extensive overview of branch circuits, covering topics such as the number of branch circuits required, voltage limitations, overcurrent protection, conductors, receptacles, and general requirements for branch circuit calculations. Article 220, Branch Circuit, Feeder, and Service Calculations. Article 220 focuses on the calculations required for branch circuits, feeders, and services. It delves into load calculations, diversity factors, demand factors, and other considerations when determining the electrical load for a building or structure. Article 225, Outside branch circuits and feeders. Article 225 deals with outside branch circuits and feeders, including those that supply power to structures like outdoor lighting, detached buildings, and similar installations. It addresses the specific requirements for these types of circuits and feeders. Article 230, Services. While Article 230 primarily deals with requirements for service conductors and equipment, it also touches on the calculation of service loads for buildings. This article provides essential information about calculating the electrical demand for the entire facility. Article 240, Overcurrent Protection. While not focused solely on branch circuit calculations, Article 240 outlines requirements for overcurrent protection, which is a critical aspect of branch circuit design. It covers topics like the selection and installation of overcurrent protection devices. Article 250, Grounding and Bonding. While Article 250 primarily deals with grounding and bonding requirements, it indirectly affects branch circuit calculations by providing guidance on the grounding of electrical systems, which can impact safety and performance. Article 310, Conductors for General Wiring. Article 310 outlines requirements for conductors used in general wiring applications, including branch circuits. It covers conductor sizing, ampacity, and related considerations. These article references within the NEC collectively provide the framework for general requirements related to branch circuit calculations. Professionals in the electrical industry refer to these articles to ensure that their designs and installations comply with the standards and regulations set forth in the NEC, ultimately contributing to the creation of safe and reliable electrical systems. In the realm of electrical engineering, the interplay of voltage, current, and power forms the fundamental basis upon which all electrical systems operate. These three vital parameters are intricately linked and play a pivotal role in branch circuit calculations, shaping the design, performance, and safety of electrical installations. Understanding the relationships between voltage, current, and power is essential for creating efficient and reliable electrical systems that meet the needs of modern society. Voltage, the driving force. Voltage, often referred to as electrical potential difference, is the driving force that propels electrons through a circuit. It is the measure of the energy carried by each unit of charge and is typically measured in volts, V. In branch circuit calculations, understanding the voltage requirements of various devices, equipment, and appliances is crucial. Properly designing circuits with the appropriate voltage levels ensures that connected devices receive the energy needed to function optimally, preventing underpowered or overpowered scenarios that could lead to inefficiencies or even damage. Current, flow of charge. Electric current is the movement of electric charge through a conductor and is measured in amperes, A. It signifies the rate at which charge flows past a given point in a circuit. In branch circuit calculations, determining the current drawn by different loads is essential for proper conductor sizing and overcurrent protection. Overestimating or underestimating current can lead to unsafe conditions, such as overheating conductors or inadequate device operation. By accurately assessing the current requirements of devices and equipment, engineers ensure that circuits are appropriately sized to handle the load without compromising safety. Power, energy and motion. Power, in the context of electrical systems, is the rate at which energy is consumed, transferred, or transformed. It is the product of voltage and current and is measured in watts, W. Power represents the energy being used by electrical devices and equipment to perform various tasks. Properly accounting for power consumption is essential in branch circuit calculations, as it affects conductor sizing, equipment ratings, and overall system efficiency. Calculating power demand accurately allows for the selection of appropriately rated components, preventing overloading and optimizing energy usage. Ohm's law, the relationship. The relationship between voltage, current, and resistance is described by Ohm's law, V equals I times R, where V is voltage, I is current, and R is resistance. This law is foundational to understanding the behavior of electrical circuits and is often used to perform calculations in various aspects of electrical engineering, including branch circuit design. Power factor, efficiency and real power. In addition to apparent power, the product of voltage and current, power factor is a consideration in electrical calculations. It reflects the efficiency of power utilization in alternating current, AC, circuits. Power factor accounts for the phase difference between voltage and current waveforms and indicates how effectively power is being used. Correcting power factor is important in industrial settings to avoid penalties from utility companies and optimize the efficiency of power distribution systems. In summary, voltage, current, and power considerations form the core of branch circuit calculations. These parameters influence every aspect of electrical design, from determining conductor size and load distribution to selecting appropriate overcurrent protection devices. A thorough grasp of the relationships between voltage, current, and power enables electrical engineers and designers to create safe, efficient, and reliable systems that meet the energy needs of today's interconnected world. In the intricate realm of electrical design, the behavior of diverse loads and varying demand patterns necessitates the incorporation of specialized concepts, diversity and demand factors. These factors are essential components of branch circuit calculations, aiding engineers in accurately assessing the electrical load that a system will experience. By accounting for the dynamic nature of load usage and the principle of not all loads operating simultaneously at full capacity, diversity and demand factors ensure the optimal design and utilization of electrical systems. Diversity factor, balancing load diversity. Diversity factor refers to the likelihood that all connected loads will not operate at their maximum capacity simultaneously. In practical terms, not all devices, appliances, or equipment within a building will be at peak consumption at the same time. The diversity factor quantifies this phenomenon, allowing designers to reduce the overall calculated load when determining conductor sizes and overcurrent protection devices. By accounting for diversity, engineers ensure that circuits are designed to accommodate the collective usage patterns without unnecessary oversizing. Demand factor, reflecting real-world usage. Demand factor goes a step further, accounting for the fact that loads may not always operate at their maximum capacity even when they are in use. This factor considers the likelihood of load variations and adjusts calculations accordingly. Demand factor values are often based on historical data or engineering judgment, reflecting the anticipated operational characteristics of specific loads. Like diversity factor, demand factor contributes to load calculations that more accurately mirror real-world usage, optimizing system design and efficiency. Peak demand and coincident demand factors, managing peaks. Peak demand refers to the highest point of electrical load experienced within a specified time frame. Coincident demand occurs when multiple loads experience their peak simultaneously. Managing these peak loads is critical to preventing system overloads. By incorporating peak demand and coincident demand factors into calculations, engineers can design systems that can handle these spikes without compromising safety or performance. Importance of accurate factors. Accurate determination of diversity and demand factors is crucial for several reasons. Optimal utilization. By incorporating realistic usage patterns, designers can avoid oversizing components, optimizing the utilization of electrical resources. Efficiency. Properly designed systems reduce energy wastage during periods of low demand or diversified usage. Resource allocation, load diversity and demand factors inform decisions about conductor sizes, transformer capacities, and other components, leading to cost-effective designs. Safety, calculations that reflect actual load behavior minimize the risk of system overloads and potential hazards. Environmental impact, efficient designs contribute to reduced energy consumption, translating to a smaller environmental footprint. In conclusion, diversity and demand factors inject a dynamic, real-world perspective into branch circuit calculations. These factors recognize that electrical loads are not constant and uniform, but rather subject to variations in usage and demand. By embracing diversity and demand, engineers create electrical systems that are not only safe and efficient but also adaptable to the evolving needs of users. In the intricate dance of electrical engineering, diversity and demand factors provide the rhythm that ensures harmonious and optimal system performance. In the intricate world of electrical design, understanding the various load types and classifications is fundamental to creating safe, efficient, and reliable electrical systems. The National Electrical Code, NEC, provides guidelines that categorize loads based on their characteristics, helping engineers and electricians tailor their branch circuit calculations to accommodate diverse electrical demands. These load classifications ensure that circuits are appropriately designed, conductors are correctly sized, and overcurrent protection devices are selected to match the unique requirements of each load. 1. Continuous loads. Continuous loads are those expected to persist for 3 hours or more. Common examples include lighting fixtures, heating equipment, and certain appliances. Branch circuits supplying continuous loads are subjected to more conservative calculations due to the sustained duration of operation. These calculations account for the potential heat buildup and help prevent overloads that could arise from prolonged usage. 2. Non-continuous loads. Non-continuous loads are expected to operate for less than 3 hours at their maximum rating. These loads, such as receptacles, motors, and air conditioning units, undergo less rigorous calculations since their intermittent operation allows time for thermal dissipation. However, it's important to consider factors such as starting currents for motors and potential simultaneous operation of non-continuous loads. 3. Motor loads. Motor loads present unique challenges due to their inrush current during startup. Calculations for motor loads must incorporate starting currents, locked rotor currents, and other motor-specific characteristics. Depending on the motor type, induction, synchronous, etc., considerations like power factor correction might also come into play to ensure efficient operation. 4. Feeder loads. Feeder loads pertain to the total load on a feeder circuit that supplies multiple branch circuits. The calculation of feeder loads involves aggregating the connected loads of all the downstream branch circuits. Feeder loads consider diversity factors since it's unlikely that all branch circuits will operate at full loads simultaneously. Accurate determination of feeder loads ensures that the feeder conductors and overcurrent protection are appropriately sized. 5. Dwelling unit loads. For residential settings, the NEC introduces the concept of dwelling unit loads. These include general lighting and receptacle loads, small appliance loads, and laundry and kitchen loads. Specific calculations, based on the square footage of the dwelling and the types of spaces, guide the design of branch circuits to accommodate the unique usage patterns in residential environments. 6. Non-dwelling loads. In commercial and industrial settings, non-dwelling loads encompass various categories such as lighting, general power, and specific equipment loads. Different types of spaces and their intended usage influence load calculations, ensuring that electrical systems are tailored to the demands of the facility. 7. Special loads. Special loads encompass a wide range of applications, from elevators and escalators to commercial kitchen equipment and medical devices. These loads often have specific requirements due to their unique characteristics, and their calculations consider factors such as duty cycles, operation modes, and power quality considerations. Understanding these load types and classifications is integral to accurate branch circuit calculations. By classifying loads appropriately, professionals in the electrical industry ensure that circuits are designed to handle diverse usage patterns while adhering to safety standards and promoting energy efficiency. In the intricate tapestry of electrical design, load types and classifications provide the framework for a seamless and optimized system.